Last time we only did 2 problems from this 2.1, even though it's supposed to be enough already. But I would like to spend more time in doing some more work, Okay. Number 29. Number 29. Find the points. Give me a second. Number 29. Find the points. Find the point of the form 2a, comma a in quadrant 3 with distance 5 from 1, 3. So pictorially, let's say I have coordinate 1, 3. Okay. And we want to find a coordinate in quadrant 3 whose distance is 5, yet at the same time it is of this form. It is of this form. Okay. Basically, you see if this is x and this is y, then x, y, then you see that y is equals to 1/2 of x. Or to be more precise, that x is 2 times y, right? X is equal to 2 times y. In other words, it has to be on line slope equals to 1/2. Maybe I move that coordinate 1, 3 a little bit. I exaggerated. Let me say that the coordinate, the line, let's say the line actually looks like this. Okay, y equals, of course, the slope is so wrong, but just to illustrate. Now, there are actually 2 coordinates on this line that has distance 5 from 1, 3. One of them here and another one here, right? To have distance 5. So in our computation later on, we will get 2 such A's. Okay, we will get 2 such A's. One of them we expect to be in quadrant 1 and the other one we expect to be in quadrant 3. But let's put that into computation solution. We start with that the distance squared equals to x2 minus x1 squared plus y2 minus y1 squared. That's the distance formula in d squared. Now the distance is 5, so I replace that d by 5. Okay, x2 is 2a, x1 is 1, plus y2 is a, y1 is 3. So I get 25 equals to 4a squared minus 4a plus 1 plus a squared minus 6a plus 9. Okay, 25 equals to 5a squared minus 10a plus 10. Subtract by 25 because it's now a quadratic equation, right? And notice that each term is multiple of 5, right? So let me divide by 5. This is basically factoring 5 out. This is basically factoring 5 out. So I get 0 equals to a squared minus 2a minus 3. And continue on the other side to save some space, right? So I do factoring now. A minus 3, a plus 1. So a equals to 3, a equals to -1. So if a is 3, then 2a will be 6, and the coordinates will be 6, 3. If a is -1, then 2a is -2, then the coordinate is -2, -1. Now, this guy here is in quadrant 1. This guy here is in quadrant 3, right? That's the one we use. Okay, so you see it's actually flowing, right? As long as you set it up right. I write the distance first, distance formula, and then I plug in numbers, right? That's number 29. And go on with number 31. Number 31, for what values of A, for what values of A is the distance between P A, 3 and Q 5, 2a greater than radical 26. We use distance formula again. Solution. Distance squared equals to x1 minus x2 squared plus y1 minus y2 squared. Now the distance is square root of 26, right? Oh, hold on. It's greater than, the distance is greater than square root of 26. So it has to be greater than, not equal to. It's greater than square root of 26. Okay, and then x1 is 5 minus x2 plus y1. Hold on, that's okay. So this is my x1. This is my 1 and 2. So this will be 2a minus 3. Then square root of 26 being squared is just 26. On the right hand side, I will FOIL. 25 minus 10 is 10a plus a squared plus 4a squared minus 12a plus 9. So 26 is less than 5a squared minus 22a plus 34. Subtract by 26, I get 5a squared minus 22a plus 8. Now, basically, I need to solve that inequality, right? I need to solve that inequality. So I start with critical number. Remember, that's polynomial inequality. Okay. Critical numbers 5a squared minus 22a plus 8 equals to 0. I do factor. I believe this is factorable. 5a minus 4 minus 2 equals to 0. So a is 2/5. A equals to 4. Those are the critical numbers. Step 2, sign graph. It's 2/5 and then 4. Both of them make it 0. And then I do testing points. When x equals to 0, the expression is positive 8. I just need positive. Okay, and and because each of those critical numbers are multiplicity of 1, an odd multiplicity, then every time I jump across that critical number, I change the sign. If the multiplicity of this critical number is odd, this critical number comes from here, the exponent is 1, it's odd, okay, then when you jump across that critical number, you change the sign. Likewise, 4 comes from a minus 4 to the power of 1. That's odd multiplicity. So when I jump across that critical number, I change the sign. Now then, step 3, solution. So I need the part that is greater than 0, which means that's positive. So it's negative infinity up to 2/5 union 4 to infinity. Okay, that's for number 31. Now 32 is actually a hard question. Oh, yeah, it's quite hard. But let's take a look. Number 32. But I want to go over this though because we will not see this anymore for the rest of the semester pretty much, but it gives us foundation to one of the topic we're supposed to cover. Okay, given A negative 2 comma 0 and B 2 comma 0, find the formula, find the equation. They say not containing radical to express the equation to express the fact that the sum of the distances from pxy to a and to b is 5. Let me give you the idea first. So we have 2 comma 0 and negative 2 comma 0. So those are two coordinates on this coordinate here and then another one coordinate here. Now we want to find all those coordinate p, x, y such that the distance to 2 comma 0 and to -2, 0. So this is our A, this is our B. Right? Now the total distance A to P plus P to B is equals to 5. Okay. Now the thing is, there are actually a lot of such coordinates. Okay. There are actually a lot of such coordinates. It may be here, maybe here. Okay. Whose distance to A plus distance to B equals to 5. Okay. Now later on, after we are done with the equation, I will show you on my graphing paper what will that look like. Okay, and that actually gives us a very important form in math. It's being used a lot in math. But let's do that first. So solution. Distance from A to P will be square root of x plus 2 squared plus y minus 0 squared, which simplifies to be square root of x squared plus 4x plus 4 plus y squared. The square root should cover all the way. Now the distance from B to P will be square root of x minus 2 squared plus y minus 0 squared. That will be square root of x squared minus 4x plus 4 plus y squared. Is it okay for now? So the distance from A to P, if I pick a random P, x comma y, that will be the one in yellow. And the distance from B to P will be the one in blue. Now, what we want to do is to find all coordinates Px that has sum of distances to A and to B equals to 5. In other words, the distance from A to P plus distance from B to P equals to 5. Okay, that's what we want to do. Then we get square root of x squared plus 4x plus 4 plus y squared plus square root of x squared minus 4x plus 4 plus y squared. Let me move this a little bit to the right. Equals to 5. That's actually the equation. Okay, that's the equation. Now the thing is, we need to get rid of the radical. How do we do that? How do we get rid of the radical? To set it up, I think to set it up right at this point, it's okay for all of us, right? Okay, the next challenge is, how do you get rid of this radical? One way is you isolate one of the radical. I basically move the, so this is the yellow one. And this is the blue one. Okay, now I move the blue one to the other side, so 5 minus square root of x squared minus 4x plus 4 plus y squared. The purpose is once I isolate one of the radical, I will square both sides. Okay, so if I square both sides, let me put a notation there. If I square both sides, then I get x squared. So on the left hand side, I get x squared plus 4x plus 4 plus y squared equals to this guy squared. I hope you notice that today I go slower, especially when I write. It's a bit tedious, I know. It's actually tedious. So instead of going fast and make little mistakes, and I have hard time to trace it back, I better go slow for every step. I do it right so that I don't need to go back anymore. Okay, just do it one time, do it right instead of like do it haphazardly and then cross our fingers that I don't make any miscomplications, right? Just do it one time, but do it right. What happened on the right hand side? I have 5 squared minus 2ab plus b squared. Okay. Now then you see that the x squared cancels. Let me mark it with a way. Is there any way? Yeah, let me mark it this way. So the x squared cancels, right? The 4 also cancels. The y squared also cancels, right? So I have, if I kind of like clear up a little bit, then I have on the left hand side 4x. Actually, this is 4x here, not 4y. This is negative 4x equals to 25 minus 4x minus 10 times square root of x squared minus 4x plus 4 plus y squared. Which, if I move the terms to the left-hand side, I will get 8x minus 25 equals to negative 10 square root of x squared minus 4x plus 4 plus y squared. Okay, so I subtract by 25 and I add 4x. Okay, you can divide by negative 10 if you like. Okay, but it's multiplication, negative 10 times square root something, right? So I will just go ahead squaring both sides right away. Square both sides. So I will get 8x minus 25 being squared equals to negative 10 times square root of x squared minus 4x plus 4 plus y squared. All of these being squared. Almost done, almost done. Now then on the left hand side we get 64x squared minus 400x plus 625 equals to negative 10 being squared is 100. Now square root of that, I keep that in parentheses, but the square root disappears. Then we get 64x squared minus 400x plus 625 equals to 100x squared minus 400x plus 400 plus 100y squared. You can see that negative 400x cancels, right? Then I will subtract by 400 both sides. And then I will subtract 64x squared both sides. That's 225 equals to 36x squared plus 100y squared. That's the equation they want. Okay, that's the equation they want. Now, let me go on a little bit discussing this. We will not see this anymore. Okay, we'll not see. It's more about the setup. So what you need to know is how to set this up and then simplify. Okay, but I want to give you some context behind this equation. If I divide both sides by 225, so 36x squared plus 100y squared equals to 225, and I make the constant becomes 1. So I divide by 225. Now then the equation becomes x squared over 225 over 36 plus y squared over 225 over 100 equals to 1. That's 25 over 9. And here, if I reduce by 25, that will be 9 over, actually, that will be 9 over 4 equals to 1. This is x squared over 5 thirds squared plus y squared over 3/2 squared equals to 1. Now notice that it fits the pattern of x squared over a squared plus y squared over b squared equals to 1.
Sorry, sir. Like, I don't really get. Isn't it meant to be 15 divided by 6 for if you're like saying square roots or like I don't
Uh,
like.
Hold on. What I did here is I reduced first. Yeah, I reduced by 9. Oh, if I reduce by 9, this should be 4. Yeah, if I reduce by 25 here, yeah, so it should be 2 here. It should be 2 here. If you do square root right away, okay, it will be 15 over 6, right?
6, yeah,
Right?
then
Okay, but then so it will be like this. But you see inside the inside that you can reduce by 3.
yeah.
So that becomes 5
5
over
over
2
2.
being squared.
Okay, yeah.
So what you did is you did the quote unquote the square root first and then reduce.
Okay,
What
okay,
I did was I reduced first and then I write it into squared form.
okay. Thank
So
you.
you can go either way. You can go
Okay,
either way.
thank
Okay.
you.
Now then, uh, if you remember from algebra 2, this is the equation of an ellipse centered at origin. Yeah, because you have x minus 0 squared, y minus 0 squared, right? Okay, centered at origin. Okay, going A units horizontally, and B units vertically, as if I'm saying the following. If you have that equation, the one in green, then it is actually an ellipse. Okay, center at origin, but then you go A units to the left, right, and B units up, down. That's what it looks like. Okay, that gives us an ellipse. Now, from algebra 2, we learned that an ellipse has two foci, two focuses. Focus, but if you make it plural, it becomes foci. Okay, that becomes foci, at which the distance from one point to the ellipse continue to the other foci, the other focus, that distance is always constant. In other words, if I go from this focus and then go here and then go here, the distance I travel will be the same to the distance I travel with other path. Okay. Now, there's a benefit of such construction. There's a benefit for such construction. But before I do that, let's see the graph of what we did earlier there. So we have, I think that's 36x squared, 36x squared plus what? 100y squared equals to 225. Enlarge that a little bit. Oops, too big. Now, screenshot. Put it back to our notes. Now, all the coordinates satisfying this equation represent the points whose distance from 2, 0 plus the distance from -2, 0 will be constant. Okay, so suppose I come from this point and I go this way, I go vertically down, right? Then I go to the other point. The total distance I travel here is the same to the total distance if I travel earlier, if I travel this way. The total distance is the same. Okay, the total distance still the same if I go this way. Now, what is the benefit of this? What is the benefit of this? The benefit is the following. First one, if Thomas, you put Thomas here, speaking, when I kind of like screaming, way, like that, right? So my voice will go to every direction. My voice will go to every direction. Okay, and because it goes to every direction, it will be reflected by the ellipse. It will be reflected by the ellipse, and it will reflect it to the direction where? To the other focus. Such that here's what happened. All my voice going to every direction, right? but the ellipse will reflect all the directions that come, all the voice coming to the ellipse from that point reflected to this point here. It will be reflected to this point there. It will be reflected to this point there. Okay, not only it will be reflected to that point, okay, my voice will arrive to that point all at the same time, because the distance of my voice traveling from here to here, the distance is the same to when it travels this way. When it travels this way, you see? Now, because of that, then when I say "oi" here, okay, then within a couple seconds, within a split of second, the person here will hear exactly the same thing, "oi," with the same magnitude. If I kind of like say "oi" like that, anybody in other place, even though they are closer to me, they will not hear that as loud compared to the person here. In other words, you can stand anywhere on this ellipse here, and you won't hear that as clear as the person who stands here. In fact, what this person here at this point is basically as if that person put his ears right next to me. Why? Because whatever voice coming out from my mouth will be reflected to that person from every direction, concentrated back to that person, okay, and not to anybody else. Okay, now with this said, then instead of Thomas screaming "oi" like that, I will just whispering. You know, when I whispering like that, now then nobody in this ellipse will hear that except that person. Okay, now that's one application. Second application. Second application is this. Imagine if I turn on some light at that point. Let's say I turn on a light bulb here. Let's say I turn on a light bulb here. Okay, so the light will go to every direction. But in any direction that light goes, it will be reflected to that point. 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 Okay. So if you imagine that this ellipse is actually mirror, if this ellipse is actually a mirror, then the light that being received at this point, the light that is being received at this point is as bright as the light that is shining at this point. Now, this becomes a method of signal transmission. If I try to transmit a data, okay, using this system, notice that if you stand somewhere in other place, you may get some data there, but it will be so dim. How to say that? Okay, let's say I say ABC, right? Okay, my A going to this direction, you receive the A maybe right now, but a split of second later, you will receive another A, another A. So when I say A like that, A, okay, then what you receive will be, you know, but longer. When I say A like that, what you receive here may be longer but weaker, because that signal comes to you not at once. Okay, while the one here will come, the signal or the voice will come to this person here all at once. So when I say A, you will hear A here, but at this point, in other point, you will hear like that. Okay, so this becomes one foundation of, they are actually going to this direction. How do you do signal processing? You transfer the data from one place to another place, okay? And nobody in between can receive the same frequency, to be more precise, the same magnitude. They may hear that, but whispering, okay? So if I say ABC, you will, see. That's what you will hear, except that when you are at the other focus, you will hear that clearly. Okay, now another thing is an ellipse is actually the shape of our planetary motion against the sun. So our sun is always located at one of the focus, and the Earth is actually revolving around the sun following the pattern of an ellipse. So if we are at the winter, for example, the December the 22nd, we are actually at the furthest distance from the sun. And around July something, I think it's June the 22nd, we are at the closest one. I think July the 23rd. Yeah, July the 23rd, approximately, we are at the closest distance from the sun. Okay, and another guy named Kepler developed further from here, saying that the distance, the distance traveled, no, not the distance, the speed you travel this far here, okay, as long as they have the same area, then the speed of you covering this trajectory will be the same to whatever region that have the same area. As long as the area is the same, then the speed, not the speed, the time you take to travel this path here, as long as the same area, then it will be the same to the time you travel this far. Okay, so a lot of things actually come into play once we get to parabola, or in this case, ellipse. Okay, now another thing is, notice that the center of this ellipse is 0, 0. Okay, you go 5/2 units to the right, 5/2 units to the left. Remember, when we convert this, we write it in that standard form, we get x squared over 5/2 squared plus y squared over what? 9/2, 3/2 squared equals to 1. So you see that 5/2 under x squared, 5/2 squared under x squared will tell us how far we go to left, right. And 3/2 squared under y squared tells us how far we go up and down. Okay, now furthermore, this actually comes from a unit circle, x squared plus y squared equals to 1. That's unit circle. Okay, and toward the end of chapter 2, we learn transformation. If you replace x by x over a, you basically stretch that horizontally by a. If you stretch that by a again here, you stretch that vertically by a. But this will give you x squared plus y squared equals to a squared. That's still a circle centered at origin with radius a. But suppose I stretch that differently. So I stretch horizontally by a, but vertically by b, then I will get ellipse. Now, this point of view gives us a notion that if an ellipse is a transformation from a unit circle. Ellipse is transformation from unit circle. Okay, it's just that I stretch that differently horizontally. Here I stretch that by 2.5, and here I stretch that by 1.5 with different ratio. If I stretch this circle with the same ratio horizontally and vertically, then I will still get a circle. But if I stretch them differently, then I get an ellipse. So far, is it okay? Now, furthermore, these are things that I think if I don't explain it in pre-calculus, nobody will explain it to you. But all of a sudden, once you get to calculus 3, for example, or actually calculus 2, then your instructor suddenly think that you're supposed to know this fact. What fact? What is the area of a circle, unit circle? What is the area of unit circle? Area of unit circle. The radius is 1. Now you told geometry, right? You don't know this? Drop the class. The area of a circle will be pi r squared, right? In this case, pi 1 squared. That's the area of a circle. Okay. Now, what happens if you have a circle with radius 2? If you have a circle with radius 2, if you have a circle with radius 2, what is the area? Then you say that area of that circle equals to pi 2 squared, right? Okay, that's correct though. But if you ever think how they get that formula, if we use the fact that the area of unit circle is pi, then how do we get the area of a circle with radius 2? Without using that formula, pi r squared. In fact, why it becomes pi r squared? Well, because of the following. The area here is pi, right? This is the area of this circle is pi. I spend so much time here because it's actually quite interesting. The area here is pi. Now, a circle with radius r is basically the unit circle being stretched by factor of r horizontally. Okay. When you stretch that by factor of r horizontally by 2, let's say by 2 units, then that becomes an ellipse. Now, what is the area of this ellipse now? Well, you stretch that horizontally by 2. So the area of this ellipse will be 2 times pi. Multiply that by 2. Now, if you stretch that vertically further by a factor of 2, then you multiply by another 2. It becomes 4 pi. In other words, if I go back and erase these, the area of an ellipse or ellipse with equation x squared over a squared plus y squared over b squared equals to 1 is given by pi a b. Why? Because that ellipse, okay, that ellipse that we have here, okay, you stretch that by a factor of, in this case, 2.5. So you multiply by 2.5. And then vertically by 1.5. So you multiply by 1.5. The area of that ellipse right now is pi times 5 over 2 times 3 over 2. That's 15 pi over 4. That's the area of that ellipse. Okay. Now, the question of the area of the ellipse is actually being solved when you are in calculus 2. Okay, so in calculus 2, they try to use calculus. Okay, they try to use calculus to compute the area of this ellipse. But if you have a good foundation in geometry, then the area of this ellipse can easily be computed by using this technique. Okay, now let me look back a little bit further. But we look back a little bit further. Okay, why is the area of a rectangle? Why is area of rectangle with length L and width W, the area equals to length times W? Of course, you have your own reasoning, right? But another reasoning possible is as the following. We start from unit square. Unit square, this is 1 by 1. Now, a rectangle is basically stretching this square. A rectangle is basically stretching this square horizontally by factor of L and vertically by factor of W. So the area that is originally 1, then multiplied by L and multiplied by W. That's how you get the area of that rectangle is L times W. That's the idea of transformation that is explained by a guy named Howard Anton. Of course, somebody else may have explained it the same way, but he is the only person I know writing calculus textbook, but having transformation in mind to help us doing the measurement fast. Okay, so other textbook, they use calculus to compute the area of this ellipse. Okay, calculus 2 instead. And Howard Anton, when he explained the same thing, he actually said that we can do this a lot easier using geometry by doing this. That's it. It's like you don't even need to know pre-calculus. You don't even need to know calculus 1. You don't need to know calculus 2. Geometry is good enough. Okay, and the way he explained these things here, the way he explained these things here is basically coming from how we can see the area of a rectangle. Okay, so this is actually a very unique way to do a problem. Okay, now I think I will stop here for this section, but if you have a chance, try to get the calculus textbook later on by Howard Anton. Howard Anton is very well known for his book in linear algebra. Now, linear algebra learns a lot about transformation. Okay, now, linear algebra is a course that you take after calculus 2. So, using linear algebra, he applies the idea back down to calculus 2 to solve a lot of calculus problems in a lot easier way. Okay, now let's go on to the next section. So I don't do number 33. I spent so much time there, but you don't need to worry about that ellipse thingy. Okay, Thomas, if I don't get it, what should I do? Well, watch this recording again, but don't worry, it will not ever show up in your test unless I ever cover that section, but I don't think I will have a chance. The next one I will cover is 2.3. We did this equation of lines before. Okay, equation of lines, 2.3, slopes, and equation of lines. Now, in my lecture, I think that's lesson 6, lesson 5, lesson 6. I went over very detailed on the lines. So we did equation of lines back in the first lesson. Lesson 1, we learned 2 points, point P and Q are given. Find the slope, which is y2 minus y1 over x2 minus y1, x1. And then find the equation of the line. And you did this type of question in your quiz 1. P and Q are in line L. Find the slope, find the equation of the line. Okay, and then in my lesson 5, or maybe lesson 6, as I remember lesson 5, I did what happened if two lines are parallel. Two lines are parallel if and only if first the slopes are the same, and second they have different y-intercept. Basically, they don't have common coordinates. Okay, and the consequence is if line 1 has equation ax plus by equals to c1, then line 2 will have the same structure but different constant. Okay, now we usually learn lines, especially if you're coming from algebra, we usually learn lines from slope-intercept form, right? We see that as y equals to mx plus b1, that's for line 1, and line 2 has the same slope, right? So it must be mx plus b2. Okay, but my explanation from lesson 5 or lesson 6, I don't remember, what happened if they are in standard form. Ax plus by equals to constant, then two parallel lines must maintain the same variable part, only the constant differ. Now, on the other hand, what happened if two lines are perpendicular? Two lines are perpendicular if the slope, the product of the slopes is -1. We usually say that the slope of one line is negative reciprocal of the other slope. Okay. Now then, another way to look at that is what happens if those two lines in standard form. Then let's say line 1 has ax plus by equals to c1. Let's say that's the equation of line 1. Now then, the other line that is perpendicular must have the following pattern. You switch the coefficients. You will switch the coefficient and change one of the sign of those coefficients. Okay, now see my explanation in my lecture. Now, with that said, then we can easily do problems as the following. Let's say, for example, number 29. So I do the one that is easily done first. Number 29. Okay, find the equation of the line containing a 3, -1 and parallel to (5x minus 2y equals to 4). Now I show you an algebra method first. So I will know if somebody really pay attention to my lecture if that person does not do it this way. Okay, it's algebra method. That person does not pay attention, or that person just doesn't care. I know how to do it, Thomas. Doesn't matter how you do it other way. Okay, so in algebra, the way you do it will be the following. Oh, let me grab that equation of that line, make it into slope-intercept form. to find the slope. And then I use that slope for the other line. So the equation of my other line, let's call this line 1. So the equation of line 2 will be y equals to 5/2 x plus constant. And then let me plug that a 3, -1 into that equation and solve for b. So end up getting the b is -17/2. So line 2 is given by y equals to 5/2 x minus 17/2. And then, oh, Thomas will want it in standard form. So let me multiply by 2. Okay, and then move the constant to the same side, to one side, and variable to the other side. That's how you do it, right? In algebra way. Now compare that to pre-calculus way of doing that. Line 1 is 5x minus 2y equals to 4. Line 2 parallel to line 1. Therefore, it must maintain the same structure except the constant. Now, how to find the constant? I plug in the coordinate 3, -1 in. So 5 times 3 minus 2 times -1 equals to c. 15 plus 2 equals to c. c equals to 17. Therefore, the equation of line 2 is 5x minus 2y equals to 17. See, Thomas, we get the same answer. Yeah, but how much time do I spend? How much time do you spend? Not to say that you may get scared every time you see fraction, right? While on the left-hand side, when I use pre-calculus method, I didn't use fraction at all. Okay. Now, how about number 32? Number 32, line 1 is given by 3x plus 2y equals to 7. Line 2 is perpendicular to line 1. Line 2 contains 5,4. Find equation of line 2. Solution. Now, because line 1 is perpendicular to line 2, then the standard form must have the following phenomena. The coefficient gets switched. You change one of the signs. So in this case, I switch the 2 and 3, right? And then I switch the sign of the 3. No, not both of the 2 and 3. You just switch one of the sign. In this case, the 3 becomes -3. The 2 stay 2. Okay, equals to constant. Now, what is that constant? I plug in the coordinate 5,4. 2 times 5 minus 3 times 4 equals to c. 10 minus 12 equals to c. So c equals to -2. Therefore, line 2 is given by 2x minus 3y equals to -2. Done. Can I use other method, Thomas, in the test? You can, but don't complain if you don't have enough time. If you keep on having that syndromes that I just want to do it different way from Thomas, okay, As long as your argument is correct, right, then I will accept that. But very likely your method will be longer than supposed to. Okay, and those are the students who used to say, Thomas, your test is way too long. If you use algebra method to do precalculus, of course, you won't be able to handle it. Okay, and next, some Mickey Mouse question, for example, number 22. Number 22, let coordinate A be 4, comma, -2. Then part A, find the equation of the line containing A and parallel to x-axis. Now, if it is parallel to x-axis, it must be y equals. What if it is parallel to y-axis, Thomas? What if it is parallel to y-axis? Then it must be x equals. Now the thing is equals what? Then just look at that coordinate. Right? Y equals what? What is the y coordinate? Y component of that coordinate? -2. What is the x component of that coordinate? 4. So if you have coordinate 4, comma, -2, 4, comma, -2 here, then the line parallel to x-axis must be y equals to. And the line parallel to y-axis must be x equals to. Okay, but other type of questions that you see here are already done on basically the first day of class. Now, there are some interesting questions, however. Number 50. Number 50. Find the equation of the line. Find the equation of the line tangent to x squared plus y squared equals to 25 at 3, 4. Let's visualize that first. But this is now the reason you need geometry for this class. So let's say we have a circle with radius 5, unit circle with radius 5. Okay, one of the coordinates on this circle is 3, 4. And you can check 3, if you plug 3 into the x, 4 into the y, you will see that's equal to 0.5. Which means that coordinate is on the circle. Okay, now the question is, find the equation of the line tangent to that circle. Find the equation of the line tangent of that circle. So this is the line that we are looking for. Okay, this is 3, 4. What is the equation of that line? From geometry, we learn something. Any line that is tangent to a circle must be perpendicular to the radius. Okay, must be perpendicular to the radius. Which means if I can find the slope of this radius, then I will be able to find the slope of that line. Okay, the slope of the radius, solution. The slope of the radius is equal to 4 minus 0 over 3 minus 0, right? Y2 minus Y1, X2 minus X1. That's 4/3. So the slope of line L will be the negative reciprocal. Right? Because it's perpendicular to the radius. Now then the equation of line L will be y equals to negative 3, 4 x plus a constant. Now it passed through coordinate 3, 4, so 3, 4 must satisfy that equation, and I use that to find my B. Okay, so 4 equals to negative 9 over 4 plus B, 16 over 4 plus 9 over 4 equals to B, that's 25 over 4 equals to B. Therefore, coming back, the equation of the line in slope-intercept form is y equals to negative 3, 4 x plus 25 over 4. Okay, we are actually done there, but if I go back, if I go on a little bit further, I multiply by 4, and then move the 3x. That's the equation of the line tangent to that circle at 3, 4. Now, once you are done with this in your calculus 3, so which is like around 1.5 years from now, 1 year if you do it in the summer, you do something in the summer, okay? But in calculus 3, they will say the following. The equation of the line tangent to x squared plus y squared equals to r squared at h comma k is given by, you replace one of the x here, you have x times x, right? Now one of the x you replace by h. It's given by hx, and then replace one of the y, that y squared becomes ky equals to r squared. In fact, I can ask you to prove this. Try to prove this using the idea from number 50. Okay, so you replace the 25 by r squared. Okay, you replace that 25 by r squared, and you replace the 3, 4 by hk. Okay, but they put it in calculus 3 because they do it another way. They do it another way. They use vectors, but that's something we could already do actually from geometry, okay, from geometry. But then some maturity level required for you to see that in more general sense. Okay, for this 2.3, that's basically what I want to go over. Let's take a break. We come back at 9:26. Let's make it 9:27. And then we will go over section 2.2, where we have more things to say actually. Okay, see you later. We will continue with section 2.2. Where we will talk about just about reflection. And then after that, I will introduce to you to some basic functions. So 2.2, they call that graph of equation, but I will focus on reflection. And later on, after that, I will introduce to you to basic functions. Now consider a coordinate, let's say 3,4. I mean, in this case, it would be better 4,3. If you watch my lecture, then you see if we reflect 4,3 with respect to the x-axis, then the reflection will be the same x, the opposite y. When we reflect that with respect to the y-axis, then the y will stay the same. The x will get the opposite. If we reflect with respect to origin, then the x will get the opposite, the y will also get the opposite. Okay, which we can summarize as the following. Reflection with respect to x-axis, what will happen? The x will stay the same. X stays the same. The y becomes the opposite. Okay, with x-axis, x the same. Y is the one get opposite. With y-axis, y stays the same. The x gets the opposite. Now, if we reflect with respect to origin, 0, 0, then both x and y gets the opposite. Okay, so this is a big notion. So here's the thing. Suppose, for example, I have this line. For example, let line L be given by 2x plus 3y equals to 5. Instead of reflecting a coordinate that we did earlier, we will now reflect a graph. Okay. Find part A, basically find the equation of the resulting the equation of the resulting line if line L is reflected with respect to part A, with respect to x-axis, with respect to y-axis, with respect to origin. What happens if you reflect that with respect to x-axis? Well, then I will change the y becomes negative y. And of course, simplify. Then I will get 2x minus 3y equals to 5. That's the equation of the new line. If you reflect this line with respect to x-axis, that's the new line. Okay. Now, what happens if we reflect that with respect to y-axis? Then the x gets the opposite. X gets the opposite. The y stays the same. So the equation becomes negative 2x plus 3y equals to 5. What happens if we reflect respect to 0, 0? Then both x and y's will get the opposite. Which, of course, we usually simplify further. We multiply both sides by negative 1. Okay, now let's take a look on what the graph look like if we actually graph them. Later on, I will copy paste this to our notes. The first equation is 2x plus 3y equals to 5. That's what it looks like. Right? Now then, if we reflect that with respect to the x-axis, the y becomes negative. You see? The purple one becomes the red one. Okay, if I reflect the original line with respect to the purple line with respect to y-axis, so I replace x by negative x, I get this. And then if I reflect the original purple line with respect to the origin, I will get negative 2x minus 3y equals to 5. Let me screenshot this. So you see, this is the purple line. This is the purple line, the original equation, right? Okay, so if you reflect this with respect to x-axis, then this point will get to here. This point will get to here. This will stay. This point will get to here. This point will get to here. This point will get to here. Right? That's the resulting graph. But what is the equation? Can you find the equation without graphing them? Right? Okay, that's actually the more a fundamental question. Can you find the result, the new equation, if you reflect this equation with respect to x-axis? And using that technique, oh, you know what, change the y becomes negative y, done, boom. And we confirm that by graphing here. Okay, we confirm that by graphing here, that the purple line becomes the red line. Right, you see that? And you can see the coloring actually here. You see, this is the color of the line. Okay, those are the colors of the line. Now, you can see also from here that if you reflect this purple line, if you reflect this purple line with respect to x-axis, then it becomes this one. What is the equation of that line? It's this. And according to the theory we have, we basically replace x by negative x. And reflecting that purple line with respect to the origin. Okay, so this guy becomes somewhere here, this guy becomes somewhere there. Okay, this guy becomes here, this guy becomes here. So as this goes that way, the reflection will go that way. Okay, we also say that reflection with respect to origin is the same to rotating 180 degrees respect to the origin. So that's also a 180-degree rotation. Okay, now this is a simple explanation, and that's why I went over equation of lines first, because I need to make sure that you know how to graph a line, right? At least review that a little bit, right? Okay, now once you can relate what happened to the lines, then we can go on even further. What happened if I have, for example, another type of graph, a graph that we don't even know what it looks like. What happened if we have, let's say, for example, I have let curve C is equal to y equals to 2x squared minus 5x plus 4. I don't know what that looks like. I don't know what that looks like, but find the equation of the reflection of C with respect to x-axis. And that gives us the idea what we will do in future. If you reflect with respect to x-axis, what do you change? We change the y becomes negative y. Of course, fast forward in future, when we write an equation of a function, we usually don't put the negative in front of the y. We usually multiply both sides by -1, so we get the opposite of 2x squared minus 5x plus 4. Okay, now that will give us a curve, but you make it upside down. You reflect that with respect to x-axis. Okay. In other words, what happened to this graph? What happened to this graph if you apply negative sign in front of it? If you apply negative sign in front of that, you basically have a parabola suddenly becomes upside down. You reflect that with respect to x-axis. Okay, that's what happened if you apply negative sign in front of a function. But why it becomes reflection with respect to x-axis? That's because we change the y becomes negative y and move the negative to the other side. Okay, that's reflection with respect to x-axis. You apply the negative. Now, what happens if we uh, want to find the equation of the reflection? Find the equation of the reflection of C, curve C, with respect to y-axis. Then we replace the x instead by negative x. Okay, and of course we simplify, and we will get 2x squared plus 5x plus 4. Okay, now let's see those two equations first using our graphing software. Have y equals to 2x squared minus 5x plus 4. That's what it looks like. Oh, that's what it looks like. It's not even crossing x-axis. So if I reflect that with respect to the x-axis, then it will be upside down, but on upside down, but below that x-axis. See, right? Okay, let me zoom it out so that we can see better. Now, of course, this graph here will be the same too if I multiply both sides by -1. So let me use new equation. That's the blue color. But if I multiply by y equals to negative, by the whole equation by -1, you will see the graph in blue and red with be identical. Okay, you see the blue graph here, and the red one is identical. Okay, that's how we also confirm that multiplying both sides of an equation by -1 does not change the shape of the graph actually. Okay, now what happens if, on the other hand, we reflect that with respect to y-axis, and then we replace x by -x, right? We replace x by -x, and we come up with something looks like this. See that? Line it up this way, screenshot, and put it on our note. Okay, so I hope I provide you a simple way to do such operation. If you want to reflect with respect to x-axis, what do you do? Reflect with respect to y-axis, what do you do? Respect to origin, what do you do? Okay. This may be too small, but I hope that's okay. And watch that. No, that's not a good way. Watch it this way. Now from the color here, then you can see which graph it corresponds to. Okay, So that's how we do reflection. Now, furthermore, how we come up with the conclusion that our textbook has. A graph definition. The graph of y equals to fx is has x-axis symmetry you say that it has x-axis symmetry if, for example, the graph of x squared. The graph of x squared has, I'm sorry, this is y-axis symmetry. The graph of x squared, y equals to x squared, has y-axis symmetry if you fold it along y-axis. If you fold it along y-axis, then the graph on the left-hand side, if you fold it along y-axis, then it will match the one on the right-hand side. Okay. Or another way to say it, it has y-axis symmetry if if you reflect that with respect to the y-axis, you get exactly the same graph. If the graph of the reflection with respect to y-axis is the same to the original graph. Right? That's what we know about a graph having y-axis symmetry. Okay? That's what we know about the graph having a y-axis symmetry. Now, however, the operation where, when we reflect with respect to y-axis, give us the same graph implies that when we replace x by negative x, basically we reflect that with respect to y-axis and simplify, we will get the same equation. So that enables us to know that the graph has y-axis symmetry without even graphing it. So you see, we know that y equals to x squared has y-axis symmetry. But how do we show that without graphing? How do we show that algebraically? Then you do that reflection. You change x becomes negative x, okay, such that now the equation is y equals to negative x being squared. Now, when you simplify, you get the same equation. Right? The reflection is the same to the original equation. Now, once we get that, then we say, oh, then it has y-axis symmetry. Okay? Now, the graph of an equation, definition. Likewise, the graph of an equation has x-axis symmetry if the graph of the reflection, if you reflect that with respect to the x-axis, you get the same graph. Now, algebraically speaking, it means in the equation, when we replace y by negative y and simplify, we will get the same equation. And finally, it has origin symmetry if replacing x becomes negative x, y becomes negative y, and simplify, get the same equation. Okay, one of if you take a look in, let's say the one I went over yesterday, not yesterday, not really yesterday. Hey, where did I save it? Okay. Hold on. I didn't save anything yesterday. Supposed to do. Oh, okay, it's here. We have the one I went over with my Monday, Wednesday class. I told you that I go over the old text, right? So let's say, for example, this one question here. How do we know that it has x-axis symmetry, y-axis symmetry, or origin symmetry? And what you do is you actually replace x by negative x, or y becomes negative y, and see what happens. Okay, so it has something to do with this later on. Let me go back to what we do today. These are the foundation when we do reflection and what we call y-axis symmetry, x-axis symmetry, and origin. Now, 2.2b, which is not really in our textbook yet. They actually discuss this much later in 2.4, but they discuss that together with transformation. I will discuss that right now, basic functions. Beside lines that's supposed to be something you know by heart already, basic functions that you need to memorize everything about this by heart. Okay, the first one, y equals to absolute x. The second, y equals to x squared. The third, y equals to square root of x. The fourth, y equals to x cubed. The fifth, y equals to 1 over x. And the sixth, y equals to square root of 1 minus x squared. These are 6 graphs that you need to memorize by heart. And in 2.4, we will do transformation on all of them. Okay, we'll do transformation on all of them. Actually, there's one more, the step function, they call that, but nah, I will not do that for now. I will not do that for now. Now, let's see what the graphs are. I will grab my graphing paper. Give me a second. And if you have your graphing paper with you, please also use that, because I need you to really know this already by heart by basically by Tuesday. Give me a second. Where's that? Okay. The first one is the graph of y equals to absolute of x. It looks like this. It looks like a V with vertex at origin. Okay. Now the slope of the right hand is 1. The slope of left hand is -1. That's what it looks like. Okay, now the important coordinates are the one I bubbles. Basically, the coordinates are 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, negative 1, 1, negative 2, 2, negative 3, 3, negative 4, 4, negative 5, 5, negative 6, 6. On Tuesday, when we come back, we will learn about transformation heavily. Okay, and we use this bubble coordinates, what I call important coordinates, and see how those coordinates transform. Okay, now then from here we see that the domain is all real numbers. You can plug in any real numbers into the X, and the range will be from 0 to positive, 0 to positive infinity. This function has y-axis symmetry, so it has axis of symmetry the axis of symmetry is x equals to 0, or we usually say y-axis. And it has vertex at 0, 0. Now, I need you to memorize this, though. I need you to memorize this. Because on Thursday, we will do something as the following. You don't need to write it down. I just give you a glimpse of what we will do later. Suppose I have y equals to negative absolute of x plus 2 plus 4. It means I move 2 absolute of x 2 units to the left, and then upside down 2 units to the left, and then upside down, and then I move up 4 units. So the graph will be 2 units to the left, upside down, up 4. So the new vertex will be -2, 4, and the graph will be like this. Okay, and then 1 unit to the right, down 1, 2 units to the right, down 2, 3 units to the right, down 3, and so on and so forth. So you can do it a lot faster instead of like, oh, you know what, let me plot coordinates. When x equals 0, what do I get? When x equals 1, what do I get? That will be way too slow. That will be way too slow. In fact, by the end of test 1, okay, you have at most 5 seconds to imagine what the graph of this equation look like. It's like you look at that, you know what to do. Okay, 2 to the left, upside down, up 4. So the vertex will be boom, boom. Okay, now you learned that transformation already in Algebra 2, but there's a chance that your instructor didn't really emphasize that at that time. Right now, I emphasize that heavily. Okay, that's why I call these basic functions. Functions that if you come to my house 3 o'clock in the morning and you slap me, Thomas, graph y equals to absolute of x, and I can grab that and go back to sleep directly. And the next day, I don't know who slapped me. Okay, in other words, you can do that in your subconscious. Okay, just like you answer 4 times 6 is 24, you don't even think about it. It's just like your subconscious, just answer it right away. Okay. The next one, y equals to x squared. The graph looks like this. The coordinates are 0, 0, 1, 1, 2, 4, 3, 9. Negative 1, 1, 2, 4, negative 2, 4, negative 3, 9. So the graph approximately something looks like this. It's a parabola. Okay, but the important coordinates are 0, 0, 1, 1, 2, 4, 3, 9, negative 1, 1, negative 2, 4, negative 3, 9. Okay, I usually say it this way. 1 unit to the left, right, go up 1. 2 units to the left, right, go up 4. 3 units to the left, right, go up 9. That's the basic graph. Then, about the domain, range, everything, you will see that whatever we have here applies the same way there. So let me just copy this. Okay, it has the same, the domain or real number, the range is 0 to infinity, axis of symmetry, x equals to 0, and then the vertex is 0, 0. Now, you're supposed to already know these two graphs by heart. Next one, square root of x. Y equals to square root of x. The graph looks like the graph looks like basically the inverted x squared. So 0, 0, up 1, right 1, up 2, right 4, up 2, right 4, up 3, right 9. So you imagine the graph of x equals to y equals to x squared, but you swap the x and the y. Okay, so that's only one of two hands of x squared, x squared like this, right? Okay, you only get the right hand, and then you reflect that with respect to this line, with respect to x equals to y line, such that the reflection becomes like this. Okay, so this part here becomes like this part here becomes here, but only one branch, only one branch, only the positive branch of that square root, only the positive branch of that square root, not the negative. Okay, So if I use negative square root of x, if I use negative square root of x, let me actually write it right below it. Y equals to negative square root of x, and then the blue one is the y equals to square root of x. Now the red one will be the one here. Down 1, right 1, down 2, right 4, down 3, right 9. Okay, so this is y equals to negative square root of x. This is y equals to square root of x. Now in both cases, the domain are or from 0 to infinity, not all real numbers. The range depends on which one you look at. Let me play with the color. The range will be 0 to infinity for the blue branch. It will be negative infinity to 0 for the red branch. Now, in both cases, they have, I call that vertex, but it is not actually a vertex. I use quote unquote here. Basically, where you start when you graph that, you start from 0, 0. Okay, this is the vertex. Now, memorize the blue graph, especially the red one is basically the reflection of the blue graph respect to x-axis, if you come to think about it, right? If you reflect the blue color with respect to x-axis, you will get the red one. Okay, it has no axis of symmetry. Okay, number 4. Y equals to x cubed. The graph looks like the vertex is 0, 0. And then the other two coordinates are on the positive side, 1, 1, 2, 8. On the negative side, -1, -1, -2, -8. This is the first graph you see that has origin symmetry. Okay, it has origin symmetry. The domain is all real numbers. Actually, as long as it is a polynomial, then the domain will be all real numbers. Now, in this case, because it is to the power of 3 to odd power, then the range will also be all real numbers. But it has a vertex 0, 0, which is also the point of symmetry. That we call that point of symmetry. If you reflect with respect to that point, then you will get exactly the same value. Or we can also say, if it has point of symmetry, then it means if you rotate 180 degrees, like if you rotate this hand here 180 degrees, then you will get this hand. And the one on the left hand, which is going down, if you rotate at 180 degrees, you will get the other hand. Okay, that's the behavior of the graph when they have origin symmetry. The fifth one. Y equals to 1 over x. Y equals to 1 over x. The graph looks like, let me rescale this, okay? But in my test, or quiz, do not rescale the grid. In other words, one grid represents one unit. Okay, one grid represents one unit. But for this one here, let me rescale it so that we can see it better. So two grids represent one unit. Okay, now then you will see 1 over x has this graph 1, 1, 2, 1 half, 3, 1 third, 1 half, 2, 1 third, 3. That's what the graph look like on the right hand side. On the left hand side, let's see. One way to help us graphing it is, do we have any type of symmetry here? And you notice that if I replace the y by negative y and replace the x by negative x, I will get exactly the same equation after I simplify it. Right? You see the phenomena? If I replace x by negative x and at the same time y by negative y, I get exactly the same equation, which means this graph has origin symmetry. The y becomes negative y, the x becomes negative x, and then when I simplify, I get the equation exactly the same to the original equation. So it has origin symmetry. Okay, so the graph has origin symmetry. Okay, so let's just reflect whatever coordinates we have there. 1, 1 becomes negative 1, negative 1. 2, 1 half becomes negative 2, negative 1 half. 3, 1 third becomes negative 3, negative 1 third. Okay, negative 1 half, comma, negative 2, negative 1 third, comma, negative 3. That's what the graph approximately looks like. Okay, basically, this point correlates to this. These points correlate to this, right? Reflected. Okay, and then these points reflected to that one. Okay, this point reflected to this point reflected to this one. Okay, now from the equation y equals to 1 over x, we can tell right away that the domain is all real numbers except 0. Right? You cannot have x equals to 0 because 1 over 0 is undefined. From the graph, you can see that the range is also all real numbers equal to 0. I mean, all real numbers except 0. But let's answer that big question. Why? Suppose I don't know the graph terms. Suppose I don't know the graph. How do I know that the graph, the range is all real numbers except 0? So let's write it down. How do we find the range of an equation without of an equation without looking at the graph. You may look at the graph and you still get the wrong answer because the graph is very limited. Like this graph here only gives you window from -3 to 3. Right? Okay, so what happens if the graph suddenly behaves erratically when x equals to 5 or when x equals to 50? Right? How do we find the range of an equation without looking at the graph? Then we do it algebraically. Okay, one of the technique is solve the equation by x and read which y are okay. So I'll solve for x first and then read which y are okay. So the work will be, well, originally the equation is 1 over x. I will solve for y. I will solve for x. So x equals to 1 over y. Now then you see 1 over y. What is y such that it doesn't become undefined? Y is okay for every numbers except when y equals to 0. Okay, I strongly recommend you to watch my lecture, my discussion yesterday with the other class, because we use this technique a lot. Okay, we use this technique a lot. Now I will use another term here. I usually call that the vertex, but I use quote unquote, which is not really a vertex. The vertex here, to be more precise, is the point of symmetry. The point of symmetry is origin. But notice that origin is not part of the graph. Okay, this origin here is not part of the graph. Okay, it just gives us the idea, oh, you know what, they have this symmetry. Once you finish graphing here, okay, you rotate this and then you will get this one here. You have that point of symmetry. If you rotate around this point here for 180 degrees, you will get exactly the same graph. If you rotate 180 degrees, so this guy becomes there. This guy becomes here. This guy becomes here, like that. Okay, but the point of symmetry is not part of the graph. Okay, now the last graph that I want to introduce to you, which I think this is the first time I introduced that to you, is y equals to square root of 1 minus x squared. This is actually the top half of a unit circle. Top half of unit circle. Why? Because unit circle has x squared plus y squared equals to 1. Right? That's a circle centered at origin with radius 1. Now, when I try to solve for y squared equals to 1 minus x squared, and I apply square root, it's supposed to be plus minus of square root of 1 minus x squared. Square root property, right? Then you will see domain and range part of that one. Okay, here. All real number except 0. So somebody asked, can you show again, Thomas, the domain and range for part 5? The domain and range this whole real number except 0. Now let me go back down. Okay. Now the thing is, if I rewrite this into y equals to the positive branch of 1 minus x squared, okay, that will refer to this part here, will refer to the top part. Only the top part. Only the top part. Okay. And if I rewrite that into y equals to negative square root of 1 minus square, that will refer to the bottom part. That will refer to the bottom part too. Okay, so looking back into, suppose I want to graph it on the coordinate plane here. Okay, let me rescale it. Let's say this is my 1. 4 grids represent 1. Okay, then my circle will be something look like this. That's what my circle looks like, right? Okay, that's what my circle looks like, but I only take the positive branch. Let me use yellow. This is the positive branch. And if you want the negative branch, that's the one at the bottom. Okay, now then, what is the domain for the yellow one? The domain will be from -1 to 1, while the range will be from 0 to 1. It has y-axis symmetry. Axis of symmetry, x equals to 0. Okay, while the bottom part will have the same domain. However, the range is from -1 to 1. I'm sorry, -1 to 0. That's the range. Axis of symmetry is the same. Okay, now I believe the suggested homework already given to you in the lecture. Okay, so try to do more problems from this 2.1, 2.2, 2.3. On Tuesday, when we come back, we will work on 2.4, and that's where we will hit, we basically start functions there, but we will do actually 2.4 and 2.5. So on Tuesday, on Tuesday we will do 2.4, 2.5, 2.4, and 2.5, maybe a little bit of 2.6. Okay, that's what we will do on Tuesday. But make sure you are really good already with this. See you then on Tuesday.